Loosely speaking, momentum can be described as a body's tendency to stay in motion. It is important to note that this is not the same concept as inertia, which is a property of matter by which objects continue in their existing state of rest or uniform motion in a straight line, unless an external force acts on them. In general, we don't calculate inertia, whereas we do calculate momentum, and it's defined as the product of a body's mass and velocity, or in mathematical notation, P equals mv. So, why do we need to know about momentum? Isn't knowing about forces, work, power, and energy just enough to do about any calculation? In short, no. Just like how the introduction of the idea of energy made it easier to analyze systems involving changing forces without knowing the details of how those forces changed as a function of time, understanding momentum allows us to understand isolated systems whose energies aren't necessarily conserved. But wait, isn't the conservation of energy one of the central tenets of physics? How can you have a situation in which energy is not conserved? To answer the first question, yes, the conservation of energy is a principle that, if violated, normally means that we've done something wrong. What I mean by having an isolated system whose energy isn't necessarily conserved is that some of the energy in the defined system is transferred to something outside of the defined system. Say, for example, we have two objects on a collision course with each other. In the real world, usually energy is released in some form of sound waves or heat via friction. The kinetic energy isn't destroyed, it's just lost to the surroundings in a different form. The key here is that the total energy in the universe is conserved. These types of collisions are known as inelastic collisions, whereas elastic collisions are ones in which energy is conserved. The fact that these different types of collisions exist mean that using work and energy alone makes calculations of velocities before and after collisions a little annoying. What's great about momentum is that unlike total energy, in an isolated system, the total momentum of a system is always conserved, and this is a consequence of Newton's third law of motion. To finish with a real-world example of the conservation of momentum's usefulness, in the 1930s when physicists were investigating beta decay of bismuth-214, they found that though total charge was conserved, momentum was just barely not conserved. Believing that the conservation of momentum couldn't be violated, Wolfgang Pauli used this data to postulate the existence of a new, almost undetectable particle called a neutrino. 26 years later, the first neutrino was officially observed, and thus this principle enabled physicists to make an accurate prediction that prompted a fervent investigation into particle physics.